In Chapter 2, we're going to look at functions, which is going to expand our list of graphs. So instead of only looking at lines, we're going to look at a broader group or class of functions. Now, functions can be thought of as a rule which assigns to each element from one set exactly one element from another set. So, for example, in the equation of a line, we could have a cost function c of x, which is defined as the linear equation 4x plus 50, or 50 plus 4x. So let's revert this back to our normal equation of a line here, so 4x plus 50. So here you have a slope of 4 and a y-intercept of 50 as a reminder. Now, many other functions are not the functions or the equations of a straight line. For example, f of x equal to x squared is called a parabola. Using the online calculator, which allowed me to graph this function, this is the equation of this parabola y equals x squared. So I defined the function as y equals x and then use the square function there. And for example, the point negative 1, 1 is on this function. So the input was negative 1. And when you take negative 1 squared, or negative 1 times negative 1, you get the output, or the y value, of 1. Similar to the cost function, if I had plugged in 25 for the value of x, 4 times 25 would be 100, and 100 plus 50 would be 150. So then we would say that the cost function is taking the value, the first element, 25, and it's mapping it to, or assigning it to, the second value, which is the y-coordinate of 150. Another example could be the square root function. So consider the function g of t equal to the square root of t. So the letter t is just sort of a placeholder. So given a value of t, for example 4, we could take the square root of 4 and get 2. Now notice in this case, we're assuming that the square root is just the positive values. When you have square roots, a lot of times, if you want the negative value, you'll put a negative symbol in front of the operator. When it's not there, it's sort of like a number. When I write down the number 2, you assume it's positive 2, even though the positive is not sitting there. Now the square root function, first of all, you can't take square roots of negative numbers. So the negative numbers you see don't have part of the graph. At 0, the square root of 0 is 0. At 4, the square root of 4 is 2, and so on. So you have this increasing curve, but as you get further out, it increases less and less. Now here's an example where you don't really have the equation of what's creating this graph, but you're just plotting points across time. So these are the first day of months versus the Dow Jones Industrial Average for those dates. And then they're just connected with lines, or really in between here, they've got all the values plotted, and then they're just connecting those with these jagged looking little line segments. Okay, but you can see that it was low back around March of 2009, but then by December it had gone back up, really from a low around a little bit less than 7,000 points to up here somewhere between 10 and 11,000 points. So this is an example of what looks to be a function, but really we don't have the equation as we had before. Now a function can be thought of as taking a value from what we call an independent variable, so that would be the role that x plays in most functions, and producing a value for a dependent variable, or a y variable, or an f of x value. So the number that you put into the equation represents the independent variable value. The number you get out is the dependent variable value. So consider a function defined as y equals 3x plus 4. Again, the equation of a line. X is the independent variable. So I give a value of x, like 0, And then what I get out depends on that value of x. So we call the y value, so 3 times 0 is 0, plus 4 is 4. So the value of y equal to 4 is the value of the dependent variable. And just remember that y and f of x are sort of interchangeable quantities. Now the domain of a function just includes all the possible values that the independent variable, or like the x variable, can take on. So what values can I give the function and actually get a correct outcome, or be able to do a calculation? The range of a function is the set of possible values that the function can produce. So you've got to consider all the possible values for the input, or the domain of the function, and what are the possible values that could be produced if you went through the entire domain of the function. Now for a linear equation, the domain typically is going to be all real numbers. I guess the exception would probably be a certain type of vertical line, in which case the domain is only one value for x. The range also typically is going to be all real numbers, again, except for the case where you have a horizontal line. But otherwise, all real numbers are possibilities for a straight line equation, as long as you don't have horizontal or vertical lines which end up impacting either the domain or the range. So let's consider the domain and range for our previous functions. So consider the parabola. Well, in this case, what did you have? Well, really, you can square any number. You can do 0, you can do negative numbers, you can do positive numbers. So the domain actually is all real numbers. So a lot of times we will write that in the notation as an open parenthesis. Okay, so the rounded bracket means you don't include the value. So we don't include, but we get as close as we can to negative infinity, and that just means you can keep going for all negative numbers, up to positive infinity, but not including it, again, because we have a rounded bracket and not a square bracket. Now the range is given as 0 to infinity, but is this the correct notation? Okay, well, think about it. If f of x equals x squared, if I put in 0, what is 0 times 0? Hopefully you recognize that 0 times 0 actually is 0, so 0 is a possibility. So we really need to write this as 0 to infinity. So I'm actually going to get rid of this notation and then put it in the correct format. So be careful on your notation. Remember, a square bracket means that is a possible value. A rounded bracket means it's not a possible value. So if I take a really big number, or a negative but large in magnitude number, like negative 10 million or positive 65 million, and I square it, it gets even bigger. So it gets bigger and bigger without bound, but yet it never can actually reach infinity. So we never include infinity in our intervals. What about our second function, our square root function? Remember, the graph is just showing the positive square roots. The general notation is that when you write a square root, if you want it to include both the positive and negative, you would put a plus and minus in front of the result. If it's not there, you assume that it's just positive. Sort of like when you write 5, you don't have to write down it's positive 5, it's just understood. So what is the domain? Well, think about the domain. What values can I put in and take the square root of? Well, I can actually take the square root of any number between 0 and infinity. I can't take the square root of negative numbers, okay, and get a real number answer. Can I take the square root of 0? Okay, so again, we need to fix the notation here. So what happens is you really need a square bracket, and then the 0 to infinity part, and then a rounded bracket. because you can plug 0 in for t. The square root of 0 is 0. Now, you can't get infinity, but as you take larger and larger numbers, you get bigger and bigger results out. But you can put big numbers in the square root. The square root of 100, the square root of 100,000, the square root of 10 million, and so on. And you can keep taking square roots of larger and larger values. So the domain is between 0 and infinity. What about the range? Well, it turns out that the range is actually the same as the domain. So really we need the rounded bracket to not be there, and we need the square bracket at 0, again for the same reason. So the square root of 0 from the domain is 0, which is the smallest value in the range. What about some other functions? Consider this function, which is a ratio of two linear functions, 15x plus 2 divided by 3x minus 1. What do you notice here? Hopefully, you can see that if I plug in 1/3 for x, 1/3 of 3 is 1, and 1 minus 1 would be 0, and now we've got a 0 in the denominator. Well, that's sort of a no-no in mathematics, right? That would produce an undefined result. So really, any other number I plug in is going to be fine, but I just can't include 1/3. So I can write that in set notation, which is the squiggly brackets, all x values such that x is not equal to 1/3, or I could write it in terms of a union of two sets. So I could say that, well, you can take any number between negative infinity up to but not including 1/3, notice the rounded bracket, union with all numbers not including 1/3 but greater than it, all the way up to basically positive infinity. So basically all real numbers except 1/3. Now the range, okay, looks like what value? Well, really, it looks like negative infinity to infinity. Okay, so if you think about it, if you put in values that are large but negative, like negative 100, you're going to get a really big number in the numerator and a big but not as big number in the denominator, so you're going to get larger and larger negative numbers. If you put in values such as 1 million, right, you'd have like 15,000,002 over, what, 3 million minus 1, 2 million, blah, 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 and nines and all the other digits, right? So you're going to get a large but positive number. So really the range of the function looks like it's going to be all real numbers, okay? And we could go back and graph our function, and except for the value at 1/3, we would be able to get any number. Well, can you get 0? Think about, can you get 0? We'll plug 0 in for x. What do you get? 15 times 0, right? So that's 0 plus 2, so that's 2 in the numerator. 3 times 0 is 0 minus 1, negative 1. So that would be 2 over negative 1, so that would be negative 2, okay? So plugging 0 doesn't work, but can you find a value of x so that you end up getting 0? Well, really the trick here is just to set the numerator equal to 0, because if you have a fraction and you have 0 in the numerator, like 0 divided by 3 equals 0. So is it true that 15x plus 2 equal to 0 has a solution? Well, yes. You could subtract 2 from both sides of that equation, divide by 15, so negative 2/15 would work. So if I plug in negative 2/15 times 15, I get negative 2, and negative 2 plus 2 would be the 0 in the numerator. The denominator, it's not 1/3, so it's not 0, so I've got 0 over a number, which would be 0. So really, all real numbers are possible from this function. What about another function? So this one is a square root, similar to this g of t function we did earlier. But what about the square root of 10 minus 5x? Now you have to be a little careful here. So 10 minus 5x, and it's the positive square root, I just can't have a negative number. As a result, what does the domain look like? Well, if I put in a number like 10 for x, that would be 10 minus 50, which would be a negative number. So numbers bigger than 2 don't work. Now if I plug 2 in, I get 10 minus 10, which is 0, and the square root of 0 is just 0. And then if I put in a negative number, then I'm going to have something like plug in negative 5. So 10 minus 5 times negative 5 is 10 plus 25, so it's the square root of 35, and so on. And as I put in larger and larger magnitude or number parts of numbers, but they're negative, I'm just going to get a larger value out for the square root. So really, negative infinity up to and including 2 are values in the domain. But any number bigger than 2, I would be trying to take the square root of a negative number, which there's no answer to. Okay? We're not considering complex numbers. If you've heard of those, we want it to be a real number. Now the range, I can get 0. Again, if I plug in 2, I would get the square root of 0 is 0. And then any positive number I can actually solve for and get. So the range turns out to be between 0 and infinity. What about a slightly more complicated model? What about y is defined as the square root of x squared plus 3x plus 2? Well, what do you think you would have to do? Well, I've got to be careful and make sure that x squared plus 3x plus 2 is not a negative number. It can be 0, it can be positive, but it can't be negative. So what do I have to do? Well, think about finding the zeros. Okay, so x squared plus 3x plus 2, let's factor that out, and what do we get? X plus 1 times x plus 2. So the zeros are at negative 1 for the first term, and negative 2 based on the second term. Now let's consider breaking the number line up into numbers that are less than negative 2, between negative 1 and negative 2, are greater than negative 1, because those are really the only 3 cases that we are concerned about. And remember, we're going to be multiplying 2 numbers together. So let's consider a number that's less than negative 2, like negative 3. Well, negative 3 plus 1 is a negative number, and negative 3 plus 2 is a negative number. So I have negative times negative, which produces what? Right, you get a positive answer out. So any number less than negative 2 will give you a positive number. Now, what if I plug in negative 2? Well, then this term is 0, so I'm taking the square root of 0, because 0 times whatever the other number is going to be 0. So the square root of 0 is 0, so that's okay. Now, what about a number between negative 2 and negative 1 on a number line, like negative 1.5? Well, negative 1.5 plus 1 is negative. Negative 1.5 plus 2 is positive. And what is the sign of a negative number times a positive number? Right, that would be a negative result. So then, if I've got a number between negative 1 and negative 2, I'm trying to take the square root of a negative number, and that answer does not exist in the real numbers. As a result, I can't have any number between negative 1 and negative 2 as part of my domain. Now at negative 1, this first term is 0. Negative 1 plus 1 is 0. The other term is non-zero, but 0 times a number is 0. So again, you have 0. Then any number bigger than negative 1, let's make it easy on ourselves, take x equal to 0. 0 plus 1 times 0 plus 2, 1 times 2 is 2. Or plug 0 into this equation. 0 plus 0 plus 2. So we're taking the square root of 2 in that case. So really, anytime I get a positive result for this polynomial or binomial, that's okay. So as long as my number is negative 2 or smaller, or negative 1 or bigger, I'm okay. I just have to exclude the numbers between -1 and -2, but not including those. So the way I can do that is say, okay, take any number from -infinity up to and including -2, and add to that any number including -1 up to but not including +infinity. So what I've done is I've taken the entire number line, except I've taken out any number between -1 and -2, because then I would be trying to find the square root of a negative number. Now the range, we've already explained how you could get 0. Otherwise, I'm taking the square root of a positive number, and actually I can make that get as big as I want to. So hopefully that gives you information on how to identify domains and ranges for functions, even if they're not linear. So be sure to look in your textbook and look at examples and make sure that you understand the terminology for this section.